them. And there are many sellers of biofilters and biotreatment filters where you can customize according to your requirements. If you tell them the waste gas composition, if you also tell them what is the desired flow that you want, then they will be able to design the system according to your specification. So we have seen different type of biofilter configurations. These are all at the full scale, but at the lab scale, if we want to do research here, we don't go for such massive scales, whereas we go for a very simple system that is made of glass or acrylic. And in those column type of reactors, we pack them with a packing material like compost, wood chips, wood bark, and we inoculate the biofilter with biomass that is usually taken from a activated sludge process. Okay, so the wastewater treatment plant sludge contains a wide variety of microorganisms, and in my opinion, they are the ideal microbial inoculum for a waste gas treatment system. You can take them, you can mix them with the packing material, and you can have them within the biofilter. And when you closely look at this photograph, you can see that it has a lot of sampling ports, as well as it has ports to collect the biomass. The reason for having such a large number of ports over the bed height is we want to know which section of the filter bed is removing the maximum amount of pollutant. Okay, so for example, if you have the waste gas that is passed from a upflow mode, then the microorganisms that are here will be receiving most part of the substrate or the carbon source, and they starts to grow much better, leading to higher removal at this section compared to this section of the filter bed. But this can of course change depending upon the microbial activity. It can also change upon the composition of the waste gas. And we also have ports here, and these are small ports which you can open with a septum, and you can collect the biomass from you can collect the packing material. And once you collect the packing material, the biofilm can be removed from the packing material, and you can do microbial community analysis. In any waste gas treatment systems, in my opinion, I would not go for a pure culture of microorganisms, because it's rather difficult to have pure cultures for a long period of time, although you can have it dominant in the system. But as long as the performance is high, and as long as the system is able to treat the waste gas, then we don't have to go for a pure culture. So that is why I always insist that activated sludge is the best inoculum for inoculating biofilters as well as biotrickling filters. They have a host of aerobic as well as anaerobic consortia of microorganisms that can convert the waste gas into either methane or VFA or other products, as well as convert them into carbon dioxide and water. Okay, so we saw a lot of open bed system, but now these open bed systems are always prone to certain operational problems. In many countries, you can see the mosquitoes, you can see rat, you can see rodents and other creatures that are occupying these filters. So these days, they don't have these open bed biofilters anymore. It's rather closed biofilters, which have much engineered system for automatic pH control, automatic relative humidity control, automatic moisture content control, automatic sprinkling of water, and you can also do a lot of you can have a lot of process control manipulations that can be done with the help of online sensors and actuators. So closed bed biofilter is one of the best that I would suggest to go if you want to operate them in the full scale. So now let me go and explain to you about the mechanism of pollutant removal in a biofilter. So when I showed you the photograph of a biofilter, of the column type biofilter, the mechanism looks very, very simple. Okay, it looks like some waste gas passes inside, it gets treated, and all the treated emission or the treated gas comes out through the top of the biofilter. But in a real biofilm system, it is completely based on chemical engineering principles of diffusion. So diffusion means the contaminant has to pass from the gas phase to the biofilm phase. So it has to diffuse through the biofilm interface. It has to come from the gas to the liquid phase. So there is diffusion as the first mechanism. And now you might also ask me the question, what are the what are the driving force for diffusion? And as you know, in this case, it's concentration and composition of the waste gas. The reason is, if the waste gas is hydrophilic in nature, it gets quite easily diffused compared to a waste gas that is hydrophobic in nature. Okay, the second mechanism is absorption. Because it contains water phase, the pollutant gets into contact with the biofilm phase, it gets solubilized, and then it gets biodegraded. But again, if you have a hydrophobic volatile organic pollutant, then of course the solubility will be less, and that would lead to less removal of pollutant in the biofilm phase. And the fourth mechanism is adsorption. Okay, adsorption can happen when you have a packing material that has large pore surface and a lot of functional groups, which will of course absorb, like activated carbon. If you use activated carbon as a packing material and you have a biofilm that is grown, a part of them, the part of the removal can also be attributed to adsorption governed process rather than biodegradation. And of course, biodegradation will also be there, and both of them will be collectively contributing to the removal. Okay, so this is the fourth mechanism, but there is another fifth mechanism which I want to tell you. It is speciation. Okay, the whole speciation chemistry is a bit complicated because we don't know what forms of species are formed from which type of pollutant. Okay, for example, if you have sulfur containing compound like hydrogen sulfide in the gas phase, when you have H2S in the gas, once it comes into the liquid phase, it can speciate to form thiosulfate, it can form bisulfite, I don't know, it can form elemental sulfur, it can form S2 minus sulfide. So there are different species which can be formed, and it can then also be biodegraded. Okay, so speciation is another mechanism that is also plays a role for for the removal process. Okay, so the mechanism basically is diffusion, absorption, biodegradation, and speciation. So for each of this, if you want to do a mathematical modeling, it's very easy to make to consider all these mechanisms and then do the mathematical modeling. So now comes the biggest question: what type of data can we collect from these systems? Okay, from a waste gas treatment system. So once you start operating the system on day zero, or once you start up, my suggestion is you start the liquid phase, because it's very important that if you want to close the mass balance, okay, if you want to close the mass balance for carbon, if you want to close the mass balance for sulfur or nitrogen containing species, then it's important that you start monitoring all the species in the gas phase and the liquid phase, and that is when you can close the mass balance. If not, it's very, very difficult to close the mass balance, and you might end up having some amount that always remains unaccounted. Okay, friends, so I have just given you some good examples of how a biofiltration system works, why it is used for volatile organic pollutant removal, and I have also explained you a little bit about the mechanism. Okay, friends, now we go a little bit to the calculations. We will have a small exercise after 10 minutes, which the organizers will send you a file. So before going to that, I will now explain to you what are the parameters that can be used for the engineering design of these reactor configurations. The first one is the hydraulic retention time. It's not the hydraulic retention time like a wastewater treatment system. We call here it as the empty bed residence time, which is the volume divided by the flow rate. Okay, it can be in terms of seconds. Seconds is the unit for empty bed residence time. So when you look at a wastewater treatment system can have a residence time or a hydraulic retention time from several hours to days. But in the case of a waste gas treatment system, it is from as low as 2.5 seconds to a maximum of 120 seconds. Okay, this is the the normal empty bed residence time of a waste gas treatment system. So it is not in terms of days or hours. It's a very high rate system. Within a fraction of a second, the waste gas will pass from the bottom of the reactor to the exit of the reactor, okay, or the inlet and the outlet of the reactor. And the second parameter is the mass loading rate or the inlet loading rate. It can be ILR or the mass loading rate, which is Q means the flow rate into multiplied by the concentration divided by the volume, which gives grams of pollutant per meter cube hour. Okay, this is the inlet loading rate. This is very similar in wastewater treatment system. We call this as the organic loading rate. I think you might be aware of this terminology. If you have COD, then you convert them into organics and you convert them in terms of organic loading rate, or what we call the OLR. And so this is the inlet loading rate, which is the gram per meter cube hour, and elimination capacity is nothing but the flow rate into the difference in concentration between the inlet and the outlet divided by the volume. It's very simple. It's just you subtract the C naught value, okay, the outlet. And the next parameter is something that you all know very well. The removal efficiency is inlet minus outlet divided by the inlet multiplied by 100. Okay, so you can please multiply by 100 so that you get a percentage. Okay, so these are some of the very simple formulas that you can use. And now you may ask me, when should I use ppm and when should I use gram per cubic meter? Okay, so please understand, ppm V is not gram per cubic meter. Okay, in gas phase systems or gas phase bioreactors, we always use gram per cubic meter. So this gram per cubic meter has a conversion of, you have molecular weight of the compound multiplied by the ppm divided by 24,776. This, the 24,776, it comes from the ideal gas law conversion at 25 degrees centigrade. Okay, so if you do this, so this is the standard conversion of ppm V to gram per cubic meter. And usually for gas phase pollutants, we always use the unit gram per cubic meter. Okay, but in some cases, some countries, they prefer ppm V. Okay, you have to say ppm on a volume basis. So if you have 200 ppm of benzene, that is nothing but 0.65 gram per meter cube because of this molecular weight. Okay, so you can see all these simple calculations. And now what we are going to do is, the organizers might have sent you an Excel file now. Okay, they might have sent you an Excel file. We will do some very basic calculations and we will see the performance of the system. Okay, so I'm going to ask you to look at the Excel file. You do these basic calculations, and I will now wait. Okay, can you see my Excel file now?
Yes, sir, we can.
Yes, sir.
Okay, yeah. Yes, can you see?
Yes, yes.
Okay, so you might have got a Excel file now, and I kindly request you to fill up all these parts. Okay, you find out what is the empty bed residence time, which is nothing but the volume divided by the flow rate. You find out what is the inlet loading rate, that is nothing but the mass loading rate. You use this formula Q. Q is given here. So the Q, it is 5, means it is 5 up to this phase of operation. Okay, if it is 10, means it is 10 up to here. It is 15, means it's 15 up to this point. So I have given you a nice data of up to 450 days. And let me now tell you what is the case. Okay, a pulp and paper mill that is located in Tamil Nadu produces several VOC emissions, among which pinene was the dominant pollutant. Therefore, the researchers at your institute have decided to test the feasibility of using a biofilter. The volume is 0.05 meter cube. Okay, so if you know what is the volume, you can estimate what is the residence time. Okay, this can be estimated. Packed with compost and ceramic beads for structural stability. The biofilter was operated at different gas flow rate. You can see the Q values are different. Okay, the Q values are different and at different inlet concentrations. As you can see here again, Ci is the inlet. The inlet is also a lot. They are all different. Then long-term experiments were carried out for around 450 days. Okay, so now you will tell me, I have given you a very nice graph. In the right side, you plot the inlet concentration, outlet concentration as a function of operation time. Okay, you calculate the removal efficiency, RE, as a function of operation time. Okay, I have given you everything. You only have to plot them. You estimate the elimination capacity and plot it as a function of the inlet loading rate, which means you plot the EC value as a function of the inlet loading rate. Okay, and that's all. And I would now then ask you, you estimate what is the minimum and the maximum values for phase 1, because phase 1 is called the startup phase. So you estimate the values for these phases, or you just estimate the minimum and the maximum for the entire operation, and you please tell me. Okay, so I'm going to give you some time now, and then we can discuss, because then once you know how to plot these simple graphs, you will be able to find out what is the threshold loading rate at which you can operate a biofilter or a biotrickling filter in practice. Okay, so please have a look at the Excel file now, and if you have any questions, you can ask me so that I can then also guide you or help you. Okay. So did you all receive the file? I see 82 participants here. Did you receive
Yes,
the
sir.
file?
Yes, sir. We have
Okay.
received it.
Okay. Okay, and in that Excel file, okay, you may have some problem. If you have some problem, for example, because my computer, the decimal point, it uses a comma. In your case, you have to check how to use it, okay? Because the decimal point is taken as a comma in my computer. So you please check that. Apart from that, if you have any questions, you please let me know. So organizers, can we have a how much time can we give for preparing this or solving this?
Sir, if you have some time in mind, because you know how long that this exercise take, uh, maybe 10 minutes to
Yes.
10 minutes to do.
Yes, I think within 15 minutes they should be able to solve to plot this, at least, to get all these values. You don't have to plot the graph. At least you can get what is the minimum and what is the maximum. Is it
Then
possible?
355
So
they will
please
be.
do these calculations now for different flow rates. Okay, the flow rates, please understand, flow rates are different from here. Then from here it is different. So you have to do this one by one. Okay, so please take your time and you do these calculations, and then you can tell me what is the value. Okay. Okay, do you have any questions? If you have any questions, you can also use the chat function and ask the questions in the chat, or you can unmute your microphone and also ask questions.
can you please formula for ILR?
Yes.
Formula for
Yeah.
ILR.
The ILR is the same as the MLR. Okay, it is the
Okay.
same.
Okay.
Okay, friends. So I think my all have now is the empty bed residence time, the inlet loading rate, the C capacity, and also the removal efficiency. So can one of you tell me what is the maximum elimination capacity of the biofilter? The maximum. What is the maximum elimination capacity of the biofilter? What is the maximum inlet loading rate, ILR, of the biofilter? And what is the range of removal efficiency of the biofilter? So there are three questions. What is the maximum loading rate? What is the maximum elimination? And what is the range of inlet concentration? Means what is the minimum and maximum removal efficiency of the biofilter?
Hello.
Yes, hello.
The first maximum value is 5800.
Okay, so you mean for the phase number 1?
ILR.
For phase, yeah, for phase number 1, yeah, you mean?
No, I'm telling figures that I got at the end of the data.
So what is the value?
5800.
Can you tell me? Okay, 5800. Excellent. Yes. Can you see my screen? You also have 5800.
I got the same
Okay,
value.
very good.
Even minimum is
Okay.
20.
Okay, very good. And what about elimination capacity?
Just one. Same thing. I got 3200.
Okay, very good. And
Last
I also hope you got 0, 100 for removal efficiency. Am I right?
Yes. I got the same thing.
Okay.
I got the same value.
Okay, friends. What about others? Because I don't hear from any of them, so I don't know whether you have any questions or you have any comments. Because I also don't see anything from the chat. So is there any questions, friends? If you don't have questions, then I will now explain you the results. Is that okay? Yeah, hello?
Okay, sir.
Okay, so I will explain the results here, which is much better. So you have to estimate the inlet loading rate and the elimination capacity, which is the most important for any bioreactor configuration that is meant for waste gas treatment. Okay, so depending upon the flow rate, depending upon the residence time, you will have different flow rates and the different inlet loading rates. So this is the typical graph that shows the elimination capacity as a function of the inlet loading rate. You can see here that as the inlet loading rate increases, the elimination capacity, it increases only up to a certain value. Okay, but in this data, it is completely a scattered data. So please don't mistake me. I just gave fake data, so you can see the different types of profile that you would get. So in this case, you can see that the inlet loading rate increases, but the elimination capacity increase only maybe up to a maximum. Okay, but then it becomes almost constant or it comes down, which means that the system operates at 100% performance only up to a certain value. Okay, so if you look at this curve, in my opinion, this reactor has a critical loading rate of 1000 gram per cubic meter hour. Okay, so 1000 gram per cubic meter hour is the design load for this biofilter. If you exceed that, obviously you will get very low performance, and we don't want a system with a low performance. So this load of 100 or maybe 1300 is called the critical rate of the biofilter. Okay, but I'm showing you a real experimental value. This is the value that we got from a different biofilter at 91 residence time, at 40.2 seconds, and also 20 seconds residence time. And you can see here that as the inlet loading rate increases, the elimination capacity increase up to a maximum, and then it starts deviating. Okay, so this is the 100% performance line, and I would very easily say here that this point or this loading rate is the critical loading rate to the system, and beyond this it is not advisable to operate the system or to design the reactor. Okay, so this is very, very important for any waste gas treatment systems. As I had mentioned to you, a biological system is often limited by its kinetics, and it always has its capacity, its maximum capacity to biodegrade any organic pollutant. And this is, as we all know, this is not a physicochemical process or an advanced oxidation process where you can go up to very high loads. But in biological system, the process is slow, the process is governed by different factors, and that is why you have to know what are the limits and what can we do to make sure that the system will operate well within the design limits. Okay, so do you have any question now with these calculations? Hello, if you have any questions about these calculations, you please feel free to ask me. But when you have time, you can also plot these graphs by yourself, which I think is also a nice small exercise. Okay, so I'm going to stop sharing the screen, and I will now share the. Okay, so we have a very limited time right now, so I would now focus on resource recovery and the practical application of biofilters for waste gas treatment system. Okay, I have 4 case studies that I would like to tell, but due to the time, I would at least cover 2 of them so that you can ask me some questions and we can have some nice discussion. The first case study that I want to show you is the removal of hydrogen sulfide under anoxic conditions. Okay, now we were talking a lot about resource recovery. We spoke about byproduct recovery. We talk about how we can convert waste gas into different compounds. But you all have to understand that even for anaerobic digestion system or any anaerobic process, the biogas that it's produced cannot be used as such in any natural grid or in directly for electricity production, because it has a lot of impurities like hydrogen sulfide, siloxane, it has oxygen, it has water vapor, it has humidity, and it has so many different compounds that are present together with the biogas. So if you want to use biogas, there are some regulations for that. So, and at the same time, you have to understand that the hydrogen sulfide concentration in the biogas is usually 0.5 to 2%. Okay, 0.5 to 2% means it's 5,000 to 20,000 ppmv, which is extremely high and which is also toxic. Okay, the reason that we don't want to have hydrogen sulfide is hydrogen sulfide is extremely corrosive, and when you start sending the biogas with hydrogen sulfide into pipelines, it will start corroding the inner surface of the pipes. And of course, the calorific value of the biogas will also decrease with all these things. So we normally try to remove all this. And one such approach, what we have found is the sulfide oxidation under autotrophic denitrification condition, which means that the nitrogen or the nitrate will serve as an electron acceptor, and the sulfur species will serve as an electron donor. And in such a case, what we tried to do was we had nitrate, which is a wastewater, and we have sulfide, hydrogen sulfide as a waste gas. So this system now, a biotrickling filter can simultaneously treat both wastewater and waste gas. So this is one of the advantage of a biotrickling filter. You can treat wastewater as well as waste gas within one single unit using the same microorganism. And this type of microorganism is called the nitrate reducing sulfide oxidizing bacteria, or also called NRSOB. Okay, and what we did was we had a nice biotrickling filter, and this biotrickling filter was filled with polyurethane foams. The polyurethane foams acted as a nice packing material because it has high specific surface area, a very good internal pore structure, and it has good moisture retaining capacity. And in our case, we passed hydrogen sulfide in a upflow mode and nitrate in a downflow mode. Okay, so when you have a upflow and the downflow, you have counter current operation, and counter current operation is always preferred because you have very good gas to liquid contact. And that was, of course, facilitated with the help of the polyurethane foam, as well as we had microorganisms that were attached onto the surface of the packing material. Okay, friends, so we measured the inlet concentration of H2S here, the outlet concentration of H2S here, and we also monitored all the nitrogen species, because I told you before, if you do any anaerobic or anoxic studies, you will have nitrate, nitrite, nitrogen, or probably you also have NO2 gas that is formed, so different, or N2O. So all this will come, but if you really want to close the nitrogen balance, or the carbon mass balance, or the sulfur balance, you need to monitor all the species in the gas phase as well as in the liquid phase. So we did a lot of experiments, but I'm showing you some of the experiments that we did. We operated the system with different N by S ratio. And now this is very similar to the carbon to nitrogen ratio, or the COD to sulfate ratio that we talk in for sulfur reducing bacteria, because sulfur reducing bacteria, they have an optimum COD to sulfate ratio. But in this case, we manipulated or changed the nitrogen to sulfur ratio during 5 phases of operation, P1 to P5. And you can see at different phases of operation, we had different hydrogen sulfide removal as well as nitrate removal. But the good thing here was the nitrate removal, or the nitrate removal was much higher than the sulfur removal. I think that is presumably because of the nitrogen to sulfate ratio, and or maybe there was a lack of the nitrogen, or what we can call in this case our electron acceptor. Okay, so under such conditions, you may have a deficit in the removal efficiency. But interestingly, what we also observed in this treatment was you will be able to close the mass balance, because we measured the nitrate, nitrogen, and the ammonia and all the other species that were present. And especially for sulfur, we monitored the sulfide in the liquid phase, and we measured H2S in the gas phase. And the second case study that I want to show you is methanol and removal under anoxic conditions. So you may ask me, where do we get this type of gases like methanol, thiosulfate, or sulfur containing compound? In a pulp and paper mill, a pulp and paper mill has a lot of cleaning activities, bleaching operation. You have the black liquor, and you also have a wide range of volatile organic compounds as well as volatile inorganic compound. So sulfur is a volatile inorganic species, and we took methanol as a volatile organic pollutant, and we want to simulate the conditions in a pulp and paper factory wastewater. So we just took 2 representative pollutants, and we wanted to see how an anoxic biofilter could be used. So this is the schematic of a biotrickling filter. We passed methanol in the gas phase. So to pass methanol in the gas phase, we took methanol as a solvent it was kept into a trough and we just bubbled it at a controlled flow rate, and the solvent vapor was passed into the biofilter. And for thiosulfate, we prepared a synthetic media with wastewater, and thiosulfate was passed in a downflow mode. So this operation was also very similar to the previous bioreactor configuration with a downflow for the liquid and an upflow for the gas, so that we could have a counter current operation. Okay, so now you can see the results here. We found very high methanol removal. CH3OH is methanol removal, which was relatively high compared to the thiosulfate, because thiosulfate was passed in a, it was not continuous mode, it was passed in a recycling mode. A recirculation mode means we did not remove any of the thiosulfate was added in batches, and it went through the biotrickling filter, it came down, then it went up and it came down. So after 3 or 4 days, its concentration got to almost zero. That is what you find here, that after a few days of operation, that the concentration of thiosulfate becomes zero, and then we add it again, then it becomes zero. So this is almost a fed batch type of operation for the liquid phase, but for a gas phase, it was continuously fed gaseous phase. And now, very similar to the previous system, we had S by N ratio or N by S ratio, but in this system, we will have carbon by sulfur ratio. Okay, so when you look at, for example, this point, you will have carbon and sulfur at a particular ratio. But when you look at this point, when sulfur is zero, you will not have any of these ratios. So this such an imbalance would also affect the microbial community and also the performance of the system. But very interestingly, in this study, when we had both methanol, that is a carbon containing compound, all this carbon was converted into volatile fatty acids. That is what we found here. And later we were also able to recover the acetic acid, isobutyric acid, butyric acid, valeric acid, and different types of acids. Okay, so all these acids were formed in this trough. So that is why we started to operate the system in a fed batch mode, so that we had a cleaning cycle. We could also recover the VFA. So this is one of the advantage of having a biotrickling filter for waste gas and wastewater treatment, because you can operate different batches for the liquid phase, and you can operate the gas phase in a continuous mode, so that you can also have one downstream processing phase where you can recover all the products that are formed. Okay, so this is just a good example of how you can treat two different pollutants, one in the gas phase, one in the liquid phase, and at the same time you can also recover volatile fatty acids. And the third case study that I would like to share with you is a case study that is also related to a pulp and paper industry, but this is not an anaerobic process. This is just an aerobic process. We wanted to simulate the removal of a hydrophilic compound, a hydrophobic compound, and an volatile inorganic compound. So that is why we went for methanol, which is hydrophilic, alpha pinene, which is hydrophobic, and hydrogen sulfide, which is a volatile inorganic compound. So we have three different types of pollutants, and we had two different types of bioreactor. One is a two-stage bioreactor. First is a biotrickling filter, and then is a biofilter. And the second system was just one biotrickling filter. Okay, so we generated all the gases, the hydrogen sulfide, methanol, and alpha pinene from in-house generators. We did not buy canisters, or we did not buy any pure gases. We just generated them in-house, and they were all passed to the first reactor in an upflow mode, and whatever that was left over, it was treated in the biofilter. So two-stage systems are highly advantageous you have when you have different types of pollutants, and you want to preferentially treat one pollutant here and one pollutant here. So in our case, we wanted to have the biofilter for pinene treatment, whereas the biotrickling filter for treating hydrogen sulfide and methanol, because it has a liquid phase, so we cannot treat a hydrophobic pollutant. Whereas the second stage, what we wanted to do was we wanted to explore the options for instead of going for two systems, we wanted to integrate them into one. So we went for a bio-trickling filter. But what we did was we took the microorganisms from these two systems, we mixed them, and we added them into this biofilter. And this bio-trickling filter was packed with PAL rings, and the microorganisms from both the systems were added here. That is nothing but it contains Rhodococcus strain. It has Ophiostoma species, which is a fungi. We have autotrophic bacteria for H2S degradation, and we also had Candida boydini, which is a methanol degrading yeast. So these are the microorganisms that we had, and this is the PAL ring that you can see that is completely filled with biomass after nearly 400 days of operation. Okay, so of course we had problems like clogging, channeling, and other things, but I will now tell you later how to overcome those issues. Okay, so now we operated this reactor, as I mentioned, for around 400 days, and during the 400 days of operation, methanol is a very easily degradable pollutant, and which is hydrophilic in nature. So its removal was substantially high. After around 80 days, it was almost 100%, except for a very few days then where it went up to 80. But methanol removal was very high in the system. But if you look at alpha pinene removal, it never reached a steady state. It was almost like this. It reached only around 80 for a few days. Then again, the concentration was fluctuating. Whereas in the case of hydrogen sulfide, although we got more than 80% removal, we were not able to maintain that for a long period of time. But still, hydrogen sulfide removal and methanol removal was comparatively better than alpha pinene removal. Okay, so now once you look at this system, the biggest problem, of course, is the hydrophobicity. But again, when you have a hydrophilic, easily degradable compound that is present with a much complex compound like alpha pinene, then the microorganisms would always go for the easily utilizable substrate. Okay, the easy utilizable substrate is methanol in this case. So probably most of the alpha pinene degrading microbial community would have preferred to consume or to degrade methanol rather than depending upon alpha pinene. So that could be one probable reason. But again, we still made this microbial community analysis with a qPCR, and finally what we found was, although the pinene degrading Ophiostoma species was dominant, it was dominant only in some section of the filter bed, whereas in different section of the different filter bed we had a lot of different colonies of microorganism, including Pseudomonas species, which we don't know from where it came. But of course, even though we added pure cultures at the beginning, at the end we had a completely different colony of microorganisms, except and of course the fungal species still remain dominant, but only in certain sections of the filter bed. Okay, friends, so now this is a much complex system because we have three different types of pollutants. And now I want to share some of my experiences with you in terms of writing the paper, because of course we all want to publish. But when we had this kind of data with, and I did not show you the microbial community analysis. We had microbial community analysis. We also had modeling for this, because this is no longer, in a chemical engineering terms, this is no longer a steady state system. In my opinion, this is a highly pseudo steady state, or it's a transient state system, because it never achieved a steady state. So we did a neural network based model. We submitted the paper, but in some cases the manuscript was rejected because they wanted to see the mass balance. Okay, they wanted to see what happened to the carbon species, what happened to the nitrogen species. And in some cases, when you have very high amount of packing material like this, for example, when you have high amount of biomass that is grown here, then there will be, of course, a pressure drop increase. Then the residence time will not be the same anymore, because we say that it's an empty bed residence time. But now with such amount of packing, the true residence time would be 10 or 15 times higher than the empty bed residence time that we are mentioning. So some of the reviewers, they would ask us to perform an RTD test, residence time distribution test with a tracer, so that we know what kind of profile do we get, and is the residence time really maintained. And in some cases, some of the papers were also rejected, like what I mentioned for VFA. We did not do a resource recovery. We only showed that VFA was produced as a proof of concept, but then the reviewers wanted us to do resource recovery. Okay, resource recovery means you need to use some synthetic resins or anionic or cationic resins, and then try to recover all these value-added products. And sometimes the reviewer would also ask you, what about the cost and life cycle impact analysis or environmental impact analysis, which I think now there is a great demand for also doing this cost analysis. Okay, cost analysis and scaling up the reactor, because there are too many publications now in the field, especially with lab scale systems. So at least when we write the paper, even though we don't go for pilot or full scale, we can at least give some perspectives for scale up. As an engineer, I think it's very easy to look for literature and to understand how can we increase the size, how can we increase the capacity, how can we put the practical, how can we apply all these systems in practice. Okay, so I think this is very important that you really consider all these operations, because in our case we went even up to 400 days of operation, but as I had mentioned to you, we did not achieve a steady state. Okay, so if you have a reactor that has very short term operation, like 40 days of operation, you please show to the, or you please make sure that you get at least a good steady state value. You also make sure that you have a value that can be repeated. Okay, so that if you repeat and you measure all the species in the liquid phase, in the gas phase, then you will be able to perform also a mass balance analysis. And now one of the innovations in this field, is we all do experiments. We have biofermenters which can also control, which can monitor a lot of variables. So with the advancements of science and engineering concepts, you can see that we can even have a mobile phone now to record all the online parameters of bioreactors. So I think if we can combine them with some very modern tools or artificial intelligence based tools, fuzzy logic or artificial neural network, then with the help of these sensors and optimization algorithms and the good process control, we will be able to control the operation of biofilters or biotrickling filters. And so now I'm talking about gas treatment, but in some countries, wastewater treatment plants, wastewater treatment plants are controlled using artificial intelligence, that you will not find any worker nearby the plant, or probably there might be only one sitting in the control room, but everything is controlled remotely using artificial intelligence, and also with the help of drone technology. Okay, the drone is very nice now. It can fly over the wastewater treatment plant. It can also monitor the gases, volatile gases, the odors, and everything that are coming from the wastewater treatment plant. So I think it's very nice to explore all these nice tools and techniques and technologies for practical application in this field of waste gas treatment, as well as, of course, wastewater and resource recovery. Okay, friends, so I would like to make a small conclusion here, that these biotrickling filters, in my opinion, compared to a biofilter, are quite versatile systems that can handle both steady state and transient state. The reason I'm mentioning to you now very proudly that the system handles transient state is because the the biotrickling filters will not fail completely. Okay, it will not break down, and it will not completely fail. It can revive itself after a period of self revival time. So if you are able to maintain the optimal operating condition, if you know what is the critical critical loading rate to the system, you will be able to operate the biotrickling filter in a very nice manner. And as I had mentioned, yeah, similar to VFAs, you can also recover many other value-added products from waste gases, and one of them is biobutanol, then biohexanol. Higher alcohols can be got from syngas. Okay, syngas is also a form of waste gas, which can be converted into different types of biofuels. And these biotrickling filters are quite robust. It has good process control. You can also apply then neural networks or fuzzy logic. Okay, and from my experience, the criticism or the comments, that you get from the reviewers will also help you to understand the system better. For example, residence time distribution, we don't normally do it during after the reactor operation, but I think it's very nice if you can use a tracer such as methane, and if you do this operation, it will also help us to understand and widen our perspectives much better. Okay, so I would like to, with that final slide, I would like to thank the Department of Energy and Environment from NIT Trichy for giving me this wonderful opportunity to share with you the experience of waste gas treatment and also the byproduct recovery. And if you have any questions, you can ask me now by voice or by chat, or if you want to contact me to know further information, you can also ask me by my email. Okay. So I think I'm very happy that I was able to share my experiences, and at least I hope that you got some perspectives on bioreactor operation, and you also get some insights onto the operation of a biofilter, biotrickling filter, and you know now that they can be applied for simultaneous waste gas treatment and also waste water treatment. Okay. So thank you.
Okay, sir. Thank you for the wonderful session, sir.
Okay, thank you so much.
Yeah, thank you, sir.
Okay, so yeah, and have a nice evening, and thank you so much.